Hey guys, all right, so you should have your calculator, a pencil, periodic table, and your notes. Normally I go with the slides, but for today, since there's so much math involved, I'm going to be using my whiteboard. All right, so starting with stoichiometry, it's all about the mathematical relationships between the amount of reactants and products inside of a chemical reaction. And we know that our chemical equation shows us what is happening inside of a chemical reaction. So we can calculate the quantities of reactants and products using a mole and mass relationship. Kind of the same way if you were using a recipe, you could scale up the recipe to make more, or you could scale it down if you didn't want to make as much. As long as you keep the ratio of ingredients the same, you're good. It's kind of the same way the chemical equations work. These chemical equations show us the ratio of substances involved in a reaction. And so this is why the balanced chemical equation is so important. And again, guys, always double check, make sure, don't assume that I'm giving you a correctly balanced equation. But this balanced chemical equation has the numerical information needed for these detailed calculations we're going to do. And what's so important, the big thing are going to be these coefficients that are going to be out in front. Those are the most important things we need inside of these conversions that we're going to be doing. The coefficients shows us how many atoms, molecules, moles are involved. So in this particular one, we have a coefficient of 1, 5, and 2. So this is saying that 1 mole of P4 will react to end up producing 2 moles of P2O5. 5 moles of oxygen react to help produce 2 moles of P2O5. 1 mole of P4 and 5 moles of O2 are reacting. So get used to seeing these coefficients as moles of the compound that they are in front. Those coefficients are key to stoichiometric calculations. They give us the numerical relationships between substances in a reaction, kind of like the ingredients in a recipe. So if I looked at this and I looked at what I just told you, 1 mole of P4 reacting to produce 2 moles of P2O5, I would say that is a 1-to-2 ratio. If I looked at the moles of oxygen reacting to produce the moles of P2O5, it would be a 5-to-2 ratio. I'm getting these numbers from the coefficients. So the coefficients from our balanced equation give us the ratios between the mole of one substance to the mole of the other. We call this the mole ratio. I could even look at what I'm reacting. I have 1 mole of phosphorus, the P4, to 5 moles of oxygen. It's a 1-to-5 ratio. It is a mole-to-mole ratio. These coefficients are my moles. And this is important because this is going to allow us to do some converting. These ratios from the coefficients can be used as conversion factors. It's going to allow us to convert from moles of one substance to moles of another. We can use these to calculate the number of moles of one substance when we give it in the moles of another. So watch. Let's say I want to use this same equation. Okay. And so they want to know so a chemical engineer wants to produce 25.0 moles of P2O5. And so they want to know how many moles of phosphorus would he burn? Well, what was my ratio between the P2O5 and the P4? Remember, it was a 1-to-2 ratio. So how would this setup look? Well, they're starting us off with 25 moles of the P2O5, and they want us to go to moles of P4. This is just going to be a cute little one-stepper. So in my bridge notation, old unit goes on the bottom, or what I'm going from goes on the bottom, 2 goes on the top. So that means mole of P2O5 is going on the bottom. Well, what am I going to? What's my new unit? Well, my new unit is what they're asking for, which is mole of P4. what I'm showing you now is I'm allowed to go from moles of one thing to moles of another. And this is where labeling in my bridge notation becomes so important. You need to keep track of what compound it is. So I'm going from moles of diphosphorus pentoxide to moles of P4. Well, what numbers do I put there? The numbers that go here depend on your balanced chemical equation. What goes there are the coefficients in front of that compound. What number is in front of P2O5? Well, I have a 2. What number do I have in front of P4? Nothing, so I assume it's a 1. And that's how I set up my problem. Please, please, please make sure that you label your bridge notation so you can see what compound you're going from, what compound you're going to. The numbers, don't always assume it's 1. These numbers come straight from your coefficients on your balanced chemical equation. So I work it out. I end up getting 12.5 moles of P4. Well, what if I wanted to go a different route with it? Let's try it this way. All right. What if I wanted to know how much oxygen is required? Let's see. I want to go from 12.5 moles of phosphorus, and I want to go to moles of oxygen. This is where I'm going from. This is where I'm going to. So I set up my bridge notation. 12.5 mole of P4. Old in the bottom. So that would be my mole of P4. What am I going to? I want to go to mole of oxygen. What numbers do I use? Look at your balanced chemical equation. What number is in front of P4? Is it going to be a 1? What's in front of oxygen? That's a 5. I've got it set up. So 12.5 times 5. That's it. So it's 62.5 moles of oxygen. So we can do all sorts of calculations now that we know this. But this is so important to have this mole to mole ratio. It's going to allow us to do so much. This mole to mole ratio, we call it the coefficient bridge. And it's determined by the coefficients from our balanced chemical equation. And it's used as a conversion factor. I can now go from moles of one substance to moles of another. And so it allows us to do so much. I can keep doing, these mole to mole problems. I'll show you one more. This is also going to allow me to do mole to mass. So we'll do one more mole to mole. So I have P2O5 plus 3 water yields 2 phosphoric acids. All right, so there's my balanced chemical equation. I did already balance it for you. Here's the question. If 25 moles of P2O5 reacts with water to form phosphoric acid, how many moles of water are required? So they want us to convert from moles of the diphosphorus pentoxide to moles of water. So set up your bridge notation. 25 moles of P2O5, because that's what they gave us. Old unit goes in the bottom. That would be mole of P2O5. Where are we going to? We want to go to moles of water. What numbers do I use? I don't know. Oh, wait. I use coefficients. This is my mole to mole ratio. This is my coefficient bridge. This is letting me go from moles of one thing to moles of something else. It's the coefficients. So in front of P2O5, I don't have a number, so I assume it's 1. In front of water, I have a 3. So then I just multiply 25 times 3. So it's going to be 75 moles of water. Easy, right? I'm not showing you anything that's too scary. So now, what if we go from moles of something to mass of something? Or we can go from mass of something to moles of something else. There's so many options. Now that we've got this new conversion factor, thanks to that coefficient bridge, that mole to mole ratio, it opens up so many possibilities. All right. So here we go. I'm going to have, oops, I'm going to try to not knock over my camera. All right. So I'm going to have, we're just going to go back to this old equation that we had been using. All right, so I've got my balanced chemical equation. Let's see. All right, so calculate the moles of P2O5. So they want mole of P2O5. That would result from the burning of 1,550 grams of the phosphorus. So my equation states calculate the moles of diphosphorus pentoxide that would result from the burning of 1,550 grams of phosphorus. So what they're asking me to do is they're asking me to go from grams of substance A to moles of substance B. Well, how do I do that? Here is the generic equation on how to do this. I start with gram of A. I can go from gram of substance A to mole of substance A, right? Because I know that 1 mole of this compound is equal to the weight of that compound. And so now that I have moles of compound A, I can go from the mole of A into the mole of B. The numbers that would go here are the coefficients from my balanced chemical equation. So I'll give you a minute to write that down if you need to. But I start with the grams that they give me of compound A. I get the molar mass of compound A because that's equal to 1 mole of that compound. This is a conversion factor we've been using all week. Now we're just adding a little bit to the problem. We're going from mole of compound A into mole of compound B. The way we're allowed to do this is by using the coefficient in front of those compounds. So for this one, here's how it would look. Start with what you're given. 1,550 grams of phosphorus. And I want to go from grams of phosphorus into moles of P2O5. Well, I need to put grams of phosphorus here. And I do my calculations and I figure out that this is 123.9 grams because I take the mass of phosphorus times 4. And we know that the molar mass of the compound is equal to 1 mole of that compound. Great. Now I'm in moles of phosphorus. They don't want moles of phosphorus. They want moles of P2O5. So I got to do one more conversion factor. Old unit goes on the bottom. I'm going from moles of phosphorus to moles of P2O5. What numbers do I put here? Well, that comes from the coefficients in my balanced chemical equation. So I've got one would go here because that's my coefficient in front of phosphorus. I have 2 as a coefficient in front of P2O5, and so that's the number I would use there. So then I would just do my math. 1,550 times 2, I would get that number, and then divide it by 123.9. And I should come up with something around 25 moles of P2O5. All right, let's do one more, and then you guys can do some practice. Look in the book, look at your notes, look at the worksheets I gave you. Some of them are worked out for you to help you out. So here's my equation. P2O5 plus 3H2O is going to give us 2H3PO4. Again, you've seen this one. All right, and they want to know how many moles of phosphoric acid can be formed from 3,550 grams of the diphosphorus pentoxide. So they gave us grams and they want moles. Grams of A to moles of B. So start with what you're given. 350 grams of the P2O5. We need to go to moles of phosphoric acid. Old unit goes on the bottom. Grams of P2O5. We know that that's going to be equal to 1 mole of the P2O5. I would have to calculate this number, right? This is the molar mass of a compound, 2 times the mass of phosphorus plus 5 times the mass of oxygen. I worked this out to be 141.9. Now I need to go from moles of P2O5 into moles of the phosphoric acid. Where do I get these numbers? I look at my balanced chemical equation. In front of P2O5, I have nothing. In front of H3PO4, I have A2. And now I'm set up. So I work this out. I end up getting about 50 moles of the phosphoric acid. It's your turn to try. Good luck.